Today, we're going to dive into the amazing world of drones. When you hear the word drone, you might picture a cool toy buzzing around the park or those epic aerial shots in movies. And you're not wrong, but modern drones are so much more than just flying cameras. They are sophisticated aerial robots, smart hardware, even smarter software to perform tasks that were once difficult, dangerous, or impossible for humans. These incredible machines are becoming essential tools in countless fields, doing good for our world in ways you might not expect. They are changing the game from the sky down. Think about it. They help farmers grow more food. They monitor crop health with special cameras. They spot problems before they become disasters. They inspect towering wind turbines. They inspect massive bridges, keeping our infrastructure safe without putting a single person at risk. They map remote landscapes for scientists. They create stunning 3D models for architects. In emergencies, they're first responders, delivering medical supplies, searching for lost hikers in dense forests. Alright, let's start at the very beginning, the basics. Before you can make a drone do amazing things, you need to understand what it is and how it stays in the air. Broadly speaking, drones come in a few main types. The most common type you'll see is the multirotor. Think of the classic quadcopter with its 4 propellers. These are great for hovering in one spot and are super easy to move around. Perfect for filming or inspections. Then you have the fixed-wing drone. It flies like an airplane. Great for covering long distances and mapping. And then there's the hybrid, the VTOL. It takes off and lands straight up and down. Then it changes to fly like an airplane. Now, no matter the type, they all share some main parts. The frame, motors and propellers, the battery. These together make up the physical base. Making it work means balancing ideas. Weight. Every extra bit of weight needs more power. More power means the battery runs out faster, making your flight time shorter. It's a constant trade-off. Range or endurance. How long it can fly or how far it can go on one charge. This is decided by the battery, weight, and how well it flies through the air. Stability. Staying in place and handling things like a gust of wind. Stability also depends on the software and sensors. Imagine trying to balance a broom on your finger. That's what the flight controller does thousands of times a second. Understanding the dance between weight, power, and control is the first step. Now that we have the body, it's time to give our drone a brain and senses. This is where the magic of electronics and hardware comes in. The most important part here is the flight controller. You can think of this as the drone's central nervous system. It's a small circuit board with a processor and sensors. It takes commands from the pilot's remote control. It mixes them with data from its onboard sensors. It makes tiny, super-fast adjustments to each motor's speed. This tireless process allows a multirotor to stay still or fly in a straight line. So, what are these critical sensors? IMU, Inertial Measurement Unit. The IMU contains accelerometers and gyroscopes. They tell the drone how it's tilting, spinning, and moving. It's the drone's sense of balance. GPS gives the drone its location on Earth. Barometer measures pressure to figure out altitude. Camera, vision for sensing and navigation. LiDAR, lasers to map the 3D environment. In projects where failure is not an option, we talk about redundancy. Redundancy is having a backup plan. A high-risk drone might have 2 or 3 of each critical sensor. For example, multiple GPS or IMU units. If one sensor gives bad data, the system switches to the backup, keeping the flight safe and stable. It's like having a co-pilot and a backup co-pilot. This idea builds trust in autonomous systems. Safety goes beyond just having extra sensors. What happens if a motor fails? What if the battery gets critically low? Or the link to the pilot is lost? The system must spot these problems and start a safe emergency procedure. For example, automatically returning to the launch point or performing a slow controlled landing. This isn't just good practice. It's a must for reliable drones. So, the flight controller is the drone's brain. It uses data from the IMU, GPS, and barometer. In critical projects, redundancy is super important. The design needs to plan for failures and trigger safe responses. Okay, we have a body and a brain. Now it's time to write the software that brings it all together. The code that gives the drone its personality and its purpose. When it comes to programming drones, a few languages are king. For rapid prototyping, scripting, high-level commands, and analyzing data, Python is a fantastic choice. It's easy to learn and has a massive community supporting it. However, when you get down to the core functions inside the flight controller, where every microsecond counts, C and C++ are the go-to languages. They are incredibly fast and efficient, which is exactly what you need for the complex calculations that keep a drone stable in the air. To manage all this code, we organize it into a software architecture. Think of it like the departments in a company where each one has a specific job. At the lowest level, you have the control layer. This is the code running lightning fast on the flight controller, handling the raw physics of flight. Above that is the navigation layer, which thinks about where the drone is and where it needs to go, planning paths and following waypoints. Then you have the perception layer, which processes data from cameras and other sensors to understand the world around it. Finally, the communication layer manages the link between the drone and the operator or a ground station. Before you ever risk a real drone in a real flight, you simulate. Simulation is one of the most powerful tools in a drone developer's toolbox. We use something called software in the loop, or SITL, where the exact same flight code that will run on the drone is instead run on a computer. This code is connected to a virtual drone in a simulated three-dimensional world. This lets you test everything. Basic stability, complex autonomous missions in a perfectly safe and controlled environment. You can even simulate failures like a motor cutting out or a GPS signal being lost. To make this complex job easier, developers often use frameworks. A great example is ROS, the Robot Operating System. ROS isn't an operating system in the traditional sense, but a flexible framework for writing robot software. It allows you to build your system out of modular packages or nodes that can be developed and tested independently. For instance, you could have one node for perception, another for navigation, and another for control, all communicating with each other. This modular approach, supported by frameworks like ROS and established autopilot software, helps manage complexity and accelerates the development of sophisticated drone capabilities. Once your drone is programmed, you need to decide how it will be controlled. This isn't a simple on or off switch. It's a spectrum of autonomy. At one end, you have fully manual control. This is where a skilled pilot is in complete command, like flying a remote-controlled plane. The pilot is responsible for every movement, every turn, and every adjustment. While it offers the most direct control, it requires significant skill and constant focus. Most modern drones, however, don't operate in a purely manual mode. They offer a helping hand to the pilot, which brings us to the next level of control. This middle ground is called assisted control. Here, the drone software provides helpful features to make flying easier and safer. For example, altitude hold automatically keeps the drone at a constant height, so the pilot doesn't have to worry about managing the throttle. Auto stabilization is another one, where the drone's flight controller works tirelessly to keep it level, even in a breeze. The most common and important assisted feature is return to home, where with the press of a button the drone will autonomously fly back to its takeoff point and land itself. These assists act as a safety net, reducing pilot workload and preventing common mistakes. At the far end of the spectrum is autonomous control. This is where the drone truly becomes an intelligent partner. In this mode, the drone is given a mission, a set of goals, and the rules to follow, and it makes its own decisions to accomplish the task. This could be as simple as flying a pre-programmed grid pattern to survey a field, or as complex as navigating through a cluttered warehouse to find a specific item. The drone is no longer just a puppet on strings. It's an agent capable of planning its path, reacting to its environment, and completing its objective without real-time human intervention. You've designed the hardware and written the software. Now comes the most important phase of all, testing and validation. This is where you prove that your drone works as it should and, more importantly, that it's safe. This process starts long before the first flight, right in the lab or on your workbench. Here, you test each component individually. You run the motors on a test bench to measure their thrust and efficiency. You check that each sensor is calibrated correctly and providing accurate data. This is your first line of defense against hardware failures, catching problems before they can get into the air. Once the hardware is ready, you move into the virtual world for extensive simulator testing. As we mentioned, simulation is your best friend. You can fly your drone through hundreds of scenarios. You can test how it handles a sudden gust of wind. You can test how it reacts to a loss of GPS signal, or if its obstacle avoidance algorithm can navigate a virtual forest full of things. Each simulated flight generates a treasure trove of data logs. These logs record every sensor reading, every command, and every decision the software made. After countless hours in the simulator, the time for real-world flight finally arrives. But you don't go to a public park and hope for the best. The first controlled field test must be done in a safe, authorized area. You start small. The first flight might just be to take off, hover for 30 seconds, and land. Then you test basic forward and backward movements. Slowly, you increase the complexity of the tests, always staying within a safe limit and being ready to take manual control at any instant. Just like in the simulator, every real-world flight is meticulously recorded for later analysis. This entire process, lab testing, simulation, and controlled flights, isn't a one-time thing. Building a powerful drone isn't just a technical challenge, it's also a big responsibility. Flying a robot in the real world means you have to follow the rules and put safety first, always. The first step is to understand and follow all the local and national rules. In many countries, this means you need to register your drone with the aviation authority, especially if it weighs more than a certain amount. These rules also set important safety limits, like how high you can fly, often around 400 feet or 120 meters, and special no-fly zones around airports, government buildings, and other sensitive areas. Knowing and following these rules is a must. Besides government rules, there are important things every responsible drone designer and operator should do. One powerful tool is a geofence. This is a virtual barrier you program into the drone, stopping it from flying into forbidden areas. If the drone gets too close to the geofence, it will automatically stop or return to a safe zone. Another critical feature is the fail-safe system. This is a set of actions the drone will automatically take if something goes wrong, like losing connection with the pilot or the battery getting critically low. A common fail-safe is for the drone to fly itself back to where it took off and land. Just like a car, a drone needs regular checkups to stay safe and reliable. Once you've gotten good at building a safe and reliable drone, you can start thinking about making it special. This is where you give your drone a specific job or a superpower. The things you can do are almost endless and keep growing every day. One of the most common uses is for mapping and surveying. You put a really good camera on it, fly it in a very exact grid pattern, and take thousands of overlapping pictures. Then, special computer programs put these pictures together to make super detailed 2D maps and 3D models. Another huge area is inspection. Drones are perfect for getting a close look at structures that are tall, far away, or dangerous to get to. Think about wind turbines, cell towers, bridges, power lines. Instead of sending a person to climb up, a drone can fly right up to the structure and use its cameras, sometimes even heat-sensing cameras or zoom cameras, to look for cracks, rust, or other damage. This is not only much safer but also way faster and cheaper. It lets companies check things more often, finding problems sooner and keeping our important structures working well. Farming is another area where drones are changing everything. In smart farming, drones with special sensors can fly over huge fields of crops. These sensors can see light that human eyes can't. They can check how healthy plants are, find spots that need more water or fertilizer, and even spot bug problems early. This information helps farmers use resources only where they are needed, which saves money, makes more crops, and is much better for the environment. Drones are also used for creative stuff, like in movies and media. They use them to get amazing shots from above that used to only be possible with expensive helicopters. And when you add AI or artificial intelligence, it can look at the information collected to automatically find specific problems or conditions. So there you have it, a complete roadmap for designing and programming drones. We've gone through the whole process, starting with the basic rules of flying key hardware parts, the software structure that makes the drone work, different levels of being able to fly on its own, tough testing, important rules, safe ways of doing things, amazing special uses. Each step builds on the one before it. The sky isn't the limit, it's just the start. Our focus: responsible creation, safe software, because with great power comes the need for great caution. We will not cover weaponized use or combat tactics. This journey is a step-by-step process. We'll break down the complete life cycle of creating a drone from absolute basics to advanced applications. It's like building with Legos. You start with the basic bricks, learn how they connect, and soon you're building something complex and amazing. We'll go through core concepts, essential electronics, the programming that brings it to life, testing and safety. It's not just about making something fly, it's about flying with a purpose, safely, ethically, and beneficially for everyone. Get ready to explore the fundamentals of drone engineering. Whether you're a curious beginner or an aspiring engineer ready to build the next generation, this guide will give you a clear path. A modern drone is a small aircraft controlled by electronics and by software. This guide explains a clear path to design and program drones for civilian uses, research, and industry. The main focus: responsible design and safe software. We will make the technology easy to understand and show you that, even though it's complex, it's something you can learn. We'll build your knowledge piece by piece to give you a strong foundation in this field. Let's start designing and programming drones for a better, smarter, safer future. There are three basic types: multi-rotor, fixed wing, VTOL. The key parts: structure, motors, battery, sensors, concepts, weight, endurance, stability. Languages like Python are used for prototypes, and C++ for flight control. The software architecture is divided into layers: control, navigation, perception, and communication. Simulation is key to testing code without risk before flying. This isn't something you can afford to skip. Before every flight, you need to do a pre-flight check, looking at the propellers for any cracks or chips, making sure the battery is fully charged and secure, and checking that all systems are working right. Over time, parts like batteries, motors, and propellers wear out and need to be replaced. Keeping a detailed maintenance log helps you keep track of your drone's health and makes sure it's always in top shape and ready to fly safely. This careful approach stops problems before they happen. Finally, we need to talk about ethics and responsibility. A drone with a camera is a powerful tool, and it's our job to use it ethically. This means respecting people's privacy. Never record or take pictures of people without their permission. When you're designing a drone, think about how it might affect society and try to use it for projects that do good. Always be open about what your drone is doing and what information it's collecting. Writing down your design choices, your testing steps, and your safety rules is a key part of being a responsible engineer and building public trust in this amazing technology. It's really important to follow the rules, like registering your drone and respecting height limits and no-fly zones. Good practices include virtual geofences and fail-safe systems. Regular maintenance and ethical use, respecting privacy, are key. Start small. Don't try a long-range delivery drone at first. Begin with simulators. Build a small, simple quadcopter. Join online communities. Read forums and watch tutorials. There's a huge global community that's generous with their knowledge. Take advantage of that, ask questions, and learn from others. This guide is just the beginning. The world of drones is always changing. New sensors, new algorithms, new uses, curiosity, practice, a commitment to safety. Keep learning and trying new things. Build with a purpose and care. The sky isn't the limit, it's just the beginning. Now go out and build something amazing. Your adventure in flying robots starts now. Phases, basics, hardware, software, autonomy, testing, rules, specialization. Put safety and ethics first every step of the way. Start with simulators, small projects, and look for communities to practice with. Keep studying and practice responsibly. There are 3 levels of control. Manual, where the pilot controls everything. Assisted, with helpers like automatic return. And autonomous, where the drone follows a plan and makes decisions. A huge part of autonomy is route planning and obstacle avoidance. Before an autonomous flight, a safe path is defined using waypoints, which are specific GPS coordinates the drone must fly to. The route plan also considers constraints like no-fly zones, altitude limits, and the drone's remaining battery life. While flying this path, the drone must be aware of its surroundings. Using sensors like cameras, LiDAR, or ultrasonic sensors, the obstacle avoidance system scans for unexpected objects, like a tree branch or a bird. When an obstacle is detected, the system must react safely and predictably, either by stopping, flying around it, or alerting a remote operator for help. It's not just about making something fly. It's about flying with a purpose, safely, ethically, and in a way that benefits everyone. Get ready to explore the basics of drone engineering. Whether you're a curious beginner or an aspiring engineer ready to build the next generation, this guide will give you a clear path. We'll take the mystery out of the technology and show you that even though it's complex, it's also easy to understand. We'll build your knowledge piece by piece to give you a strong foundation in this field. Let's start designing and programming drones for a better, smarter, safer future. The real magic happens when you bring together these special apps with artificial intelligence and data analysis. A drone checking a power line doesn't just send hours of video for a person to watch. Instead, an AI program, either on the drone or in the cloud, can look at the video right away. It automatically finds and marks problems, like a frayed cable or a broken insulator. The information from a farm drone can be fed into a learning program to guess how much crop will grow. This mix of flying on its own, special sensors, and smart data analysis is what turns a simple drone into a powerful automatic solution. Drones are becoming experts in things like mapping to make 3D models, checking buildings, helping with farming, and making movies. Working with AI lets them look at the data they collect to automatically find problems or specific conditions. Choosing backup hardware. Programming strong safety routines. Following rules and respecting privacy. Being committed to creating responsibly. Building systems that work well, are predictable, and safe. This way of thinking is what makes new robot ideas possible. Start small. Don't try to make a long-range delivery drone right away. Begin with simulators. Build a small, simple quadcopter.